Okay, so we're going to now talk about a new topic called moment and finding the center of mass of an object. And this is something you engineering majors, you will be working with a lot in some of your future classes. Knowing where the center of mass of an object is a very important idea. So first, a little physics review. Some of you have not started your physics yet here at UC Davis. Some of you may have some physics experience from high school. So weight is your product of mass times the acceleration of gravity. People get confused a little bit between a force and a mass. A weight is a force. Force, the definition of force is mass times acceleration. Mass is constant for an object. You could think of mass, there's a scientific definition of it, but sort of maybe more intuitively, think of a mass as sort of the accumulation of all of the atoms in an object. That would be the same whether that object was on Earth or if it was on the moon, for example, or in space where there is no gravity, well, very little. So your mass would stay the same whether you were on the moon or if you were on Earth. Your weight, of course, would change because the acceleration of gravity differs, right? It's stronger on the Earth. The Earth has a bigger mass than the moon. You would weigh more. So mass is constant. Your weight depends on gravity. Let's just summarize it like that. Okay. So now let's talk about the idea of torque. Slide this up a little bit. So when you apply a force to what we call a lever arm at a certain distance from a point which we call the fulcrum, a torque is produced, which causes the lever arm to rotate about the fulcrum. So I sometimes think of this, it almost looks like a diving board. If you've ever been on a diving board that's attached at one point here, if you're standing here at the end of the diving board, and imagine it was free to rotate, unlike diving boards which bend, you would cause the diving board to move downward, right? And that's a function of two things, not only how much you weigh, your force, your weight, but also how far you're standing on the diving board, right? If you've done this before, if you stand a little bit closer to the fulcrum, the board is not going to rotate quite as much, right? It's when the bigger the distance is, you create a bigger torque. So torque is the product of force times the distance to the fulcrum. Another example, kind of illustrating torque, here's a pair of wire cutters. The fulcrum, you could imagine, is right here. It's connecting the two levers that I use to squeeze it. And in your own experience, you probably realized if I apply a squeezing force at the very end of the handle, I don't have to squeeze very hard. But if I move my fingers in closer to the fulcrum, I have to apply a greater force to get this to squeeze. And that's because the torque I'm producing is not as great when my distance is close to the fulcrum as when it's further away. You get a greater torque. Okay. Now, torque is the product of force times the distance to the fulcrum. We're going to talk a lot about moment, and moment is based on that very same idea. But moment is the product of mass times distance to the fulcrum. So we take gravity out of the equation here so that it doesn't matter what gravity is. Moment will be mass times distance to the fulcrum. Okay. And if you want to get a torque, you could just multiply by the acceleration of gravity if we're talking about a weight. So back to mass. Mass is weight divided by the gravity acceleration. And so some units for that If you're in the metric SI system, it would be measured usually in kilograms. A lot of people are not aware of this, but if you're in imperial units, what we use in the US, your weight divided by the acceleration of gravity, which is about 32.2 feet per second squared, it comes out to be in units of, we call that slugs. So if you have a 150-pound person, you would have a mass of around 5 slugs. All right, so now what we're interested in here, the center of mass. Let's think of this as a balancing point. So imagine you had a fulcrum with a lever arm with some masses applied at different distances from the fulcrum. I got a 5 kilogram, a 3 kilogram, and a 2 kilogram mass applied at various distances. Okay, so that's going to cause the lever arm to rotate in a clockwise direction. So if we wanted to counteract that and keep this system in equilibrium, we would use, this could be balanced by, if you put something underneath it, right, it's going to have an upward mass of the sum of these masses. Okay, so that totals up to 10 kilograms. So if I were to put something to hold it up, it would be counteracted with 10 kilogram mass at a certain distance, right? If I put this 10 kilogram mass all the way over here, I might actually overcompensate and cause the system to rotate counterclockwise, right? If I don't put it far enough, these moments created by these masses might still cause the lever arm to rotate. So there's a certain place where this mass could be applied and the system would be in equilibrium. And in fact, the way to think of it is where, if I put this at the correct spot, I could then take away the fulcrum and everything would balance. Okay, so it is kind of like what we're doing here is kind of like finding the center of mass of an object, like a pen. Where would I balance this thing? This is hard because it's not, where would I balance it? Where's that point where the pen balances without falling on either side? That's what we're looking for. That's the center of mass. So how we find this, to balance, the sum of our moments have to equal 0. And what I mean by the sum of the moments, all of these moments on the top are causing the system to rotate clockwise, and let's call that positive moment. So we'll take 5 kilograms times 1 meter, mass times distance to the fulcrum, plus 3 kilograms times, this would be 4 meters, and that 2 kilograms times the full 10 meters. Notice, by the way, that is producing 20 kilogram meters of moment, which is more than either of these two. Even though that was the smallest mass, because it's applied at the furthest distance, it's actually creating more moment than the other two. Now, we'll decide any masses applied that cause the system to rotate counterclockwise, we'll treat that as a negative moment. And so that would be the 10 kilograms times this distance that we're looking for, which we'll call x bar. And that's the center of mass. And we want that to come out to be 0 so that there is no net moment in the system. So if we solve for x bar, I didn't simplify this all out for a reason here. So you would get all of those positive moments divided by 10 kilograms. The units, the numerator would be kilogram times meters, the denominator is kilograms, those would cancel, and I'd be left with a distance, which would come out to be 3.7 meters. So that would be the center of mass of that system. That would be where you would balance all of those masses. Now, it's kind of revealing here then, what is in general, how we will find the center of mass. What is the numerator this is the sum of all of the moments applied to the system. And what is the denominator? That 10 kilograms was the sum of all of your masses. So this is going to be our basic formula for finding center of mass. It's the sum of the moments divided by the sum of the masses. All right, let's look at an example now. So let's say we have a thin rod, a length of 10 centimeters, with a density, delta is x squared grams per centimeter as measured from the left end. So the way to think about this, you've got a thin, when they say thin, here's what they mean. In the real world, density is mass divided by volume, of course, right? And we will get there. Right now, to sort of develop these ideas, we're going to think of this as a one-dimensional object. This is a thin wire, maybe, that actually has no thickness to it. It only has length. Now, of course, that's not realistic either, but we're just, so it's more, this is more just a theoretical example, but we're going to use this to sort of build some of our ideas for finding real-world center of masses. But you could picture this. Okay, the density, according to this density formula, the density, if we call x equals 0 the left end, the density has no density, it has no mass right there. And when x is 10, the density is 10 squared, 100 grams per centimeter. So it's, you could think of this as a thin wire that's getting heavier and heavier as you move towards one end. And I was trying to think of something kind of like that. So I have a pair of scissors here. Where the density is not the same, unlike maybe something like a pencil, where it's, you know, roughly for most of the pencil, the density is the same, and as you might expect, the balancing point would be in the middle somewhere. Of course, you lose some mass here when the pencil's sharpened, and you've got some extra mass here with the eraser, so it's not perfect, but it's roughly constant density. Something like a pair of scissors, I mean, you've got different shape all over, right? And the center of the scissors, it looks like, is right about at the fulcrum, but because this isn't constant density, I'm not going to imagine it's going to balance right in the middle, and it won't. It's going to fall down. Okay, and in fact, it's a little deceiving. It looks like there's more mass here, but this is plastic, and it's much lighter. This is metal here. So the true balancing point, I'm actually going to have to, it's actually going to lie over here a little bit. Not quite in the center. Okay, so that's kind of what I'm expecting here. It's heavier on one end than the other, so I would not expect the balancing point to be in the middle unless it had constant density. Okay, so density is mass divided by length, which means for this problem, we're going to think of mass as density times length. Okay, and our formula for the center of mass, we want to find it's the sum of the moments, and moments is mass times distance to the fulcrum divided by the mass. Since the mass is constantly changing, we have to use an integral. So the idea is we take a small little piece of this wire at some distance x from the left end, we take a little thickness of it. The mass of that is the density times the length. So it would be density times our little tiny increment, that would be dx would be the length. And we multiply that by the distance to the fulcrum, which is x centimeters. And we're going to integrate that from 0 to 10. And when you integrate that, oh, it's x squared, I'm sorry. This was x squared. No. The density was x squared, that's right. The density was x squared here. And so that turns out to be x cubed, and so the antiderivative of that would be x to the 4th over 4, which would give you 10 to the 4th over 4. There should be, no, that's it, okay. Whereas the denominator is just the integral for mass, which is density times length, and we're going to integrate that from 0 to 10. Your density was x squared. That integrates to x cubed over 3. If you plug in from 10 to 0, you get 10 to the 3rd over 3. And if you simplify that, you get 7.5 centimeters. So the actual balancing point would be 3/4 of the way, right? Remember the length was 10, so about right there is your balancing point. All right, now let's step this up one dimension. We're going to now imagine we have a thin plate. So this is a two-dimensional object now, okay? Of course, a real plate, a real object would be 3 dimensions. So when we say thin, we mean infinitely thin, okay? Sometimes they'll ask for the centroid of an object, and if they say centroid, it's implied that it has constant density. So nothing needs to be provided. We're assuming this thing is constant density throughout the region, okay? In fact, when that's the case, if you have constant density, as I mentioned earlier, you can kind of use your intuition and imagine if this was a thin plate, where would it balance, right? Where would I stick, if I could pull this thing out and balance it on my finger, where would it balance? And it looks like it would probably be somewhere right in there. And the center of mass now has 2 coordinates. There's an x coordinate and a y coordinate. So we're looking for x bar and y bar. For thin plates, your formula for x bar is going to be the moment about the y-axis, I'll explain that in a second, divided by the mass. And y bar is the moment about the x-axis divided by the mass. Okay, so it's the same general definition, right? It's the sum of the moments divided by the mass. So the way you can think of this, think of these, how we're going to find it and how we'll define moment about the y-axis and the x-axis is essentially we're going to think about this plate as a door attached. Right now, let's imagine it attached to the y-axis. So imagine this thing could rotate around the y-axis, this plate. I tried to draw a little mini plate here. Imagine this was the y-axis and this thing could swing around the y-axis, okay, like this. And this thing has mass, and because it has constant density, all points along a thin vertical strip of this door, if you will, has a certain mass that is applied at a certain distance. So this whole y-axis is like your fulcrum. It's rotating around that. So if this thing was hanging, for example, this mass would cause this to want to rotate around the y-axis. So the moment about the y-axis is defined as mass times distance to the y-axis. Of course, your mass would be along a thin vertical strip. And when we do the moment about the x-axis, then we're going to, and that's going to help. The moment about the y-axis, remember, this is related to x bar. This is going to tell you how far from the y-axis you would need to place your finger to have this plate balance perfectly. And then we're going to switch it up to find y bar, how high you would need to place your finger to get this thing to balance. We're going to switch it around now and imagine that this plate is allowed to rotate around the x-axis. So imagine your plate here could rotate this way around the x-axis. Okay. So what would moment be defined as? Well, mass times distance to the x-axis. I think I said y-axis before. Rotating around the x-axis, right? So the x-axis is your fulcrum. So moment would be defined as mass times distance to the x-axis. At all points that are the same distance to the x-axis would lie on a thin horizontal strip. Okay, and you would add up all of the moments, all of the horizontal strips, mass times the distance to the x-axis. Okay, so that's where those definitions are built on. So here we go. Moment about the y-axis is mass times distance to the y-axis. That will be x. Whoops, let's zoom that in a little bit. And we know mass is delta times area this time, instead of delta times length on the previous one. So to find the area, I would do top minus bottom, just like we were doing area, root x minus x, technically times dx right here for the area of that thin strip, and then distance to the y-axis would be x. And you would integrate this throughout the region from x equals 0 to x equals 1, which is where they intersect. Now delta is constant, right? It said centroid. I still recommend, some teachers will have you replace delta with 1, because if delta is constant, it could be any number. And so if you make it 1, then it just disappears. I like to keep it in there. I want people to always remember that that mass is delta times area, or delta times volume, or delta times length. I don't want you to forget that it should be there. So, but if it's constant, we'll just leave it as delta, and I'll pull it out of the integral. If you distribute the x and integrate this from 0 to 1, you will get 1/15 delta for the moment about the y-axis. Moment about the x-axis is mass times distance to the x-axis. This is the situation where we're using horizontal strips. So right here. So we have to do, for delta times area, we're going to do, because the distance to the x-axis is y, then we want to express our area in terms of y. So we're going to do right minus left. This was y equals x, also known as x equals y. The left function is y equals root x, also known as x equals y squared. So right minus left, dy times y from 0 to 1. Again, pull out the delta. And if you distribute the y and integrate, you would get 1/12 delta. And then the mass is the easiest integral. That's just delta times area. And you can do vertical cross sections or horizontal. Probably a little more familiar with vertical cross sections. We seem to use that more often. So it's just delta, and then your vertical strips are top minus bottom dx. And if you integrate this from 0 to 1, you will get 1/6 delta. So then we have everything we need. X bar is moment about the y-axis divided by mass. 1/15 delta divided by 1/6 delta. The deltas cancel, right? And that's right. But I still like people to put it there, so you realize it should be there. And those cancel, and I get 6/15 or 2/5. Y bar is moment about the x-axis divided by mass. 1/12 delta divided by 1/6 delta gives me 1/2. And so my center of mass, it's a coordinate, would be 2/5, 1/2. And again, you could think of that as your balancing point. If you were able to take that thin plate and find that point 2/5, 1/5 right here, you could, in theory, balance that plate right on your pen, right at that point. You could put it right underneath and it would balance. Let's do one more thin plate. This time, our thin plate does not have a constant density. The density is x squared. Okay. And our plate is the area between y equals 3 minus x squared, y equals 2x, and the y-axis. So if the density is not constant, let's think about this now. It's a function of x. So any point right here along the y-axis, any point right here, your density is actually 0, right? Because it's x squared. But at this point right here, where x is equal to 1, your density would equal 1. And of course, at all x values between 0 and 1, your density would be that x value squared. So you can think of this kind of like the thin wire we did earlier, as a thin plate that's getting heavier as you move to the right. So the balancing point is not necessarily where you would think it would be if it had constant density. Same definition applies though. The mass is the easiest integral, so might as well start with that one. Mass is density times area. We're going to describe the area with vertical cross sections. So any vertical cross section is top minus bottom times dx. And this time density is x squared, so we include that. And to actually evaluate it, you'd want to distribute it, integrate from, in this case, 0 to 1, and you would get 3/10 for that. Moment about the y-axis is mass, density times area, you have that there, times the distance to the y-axis, which is x. So that means we're using vertical strips again, okay, right? Because vertical strips, the distance to the y-axis is constant, and that distance is x. Which means for area, I can stick with the same formula I did here, density times area times distance to the y-axis, which is x. You would have to distribute not only the x squared, but also the x, and get a result of after working through the integral, I got 11/60. Now here's where we run into trouble. Moment about the x-axis is defined as mass times distance to the x-axis. And the distance to the x-axis is y, right? All points that are the same distance to the x-axis is y. Now the trouble with that is mass is density times area, but my density was given as x squared. So the issue here is my integral is going to have two variables, and we can't handle that right now. Get to 21D, we will be able to do this, but right now we can't do an integral in terms of two variables. So in this case, what we're going to use is an alternate formula for the moment about the x-axis. Because our density is x squared, we need to keep this integral in terms of x, which means we need to use vertical cross sections. Okay. Now, because my density is just a function of x, at any particular x value, if I use a vertical strip, this is not the same picture, obviously. I'm just doing a general formula for a moment about the x-axis, an alternate formula. So I'm just making up a thin plate here of two functions, f of x and g of x, and we'll apply it to our problem. But if the density is a function of x, then if you consider a thin vertical strip at a particular x value, the density of that thin rectangle is constant, right? Even though it won't be the same density as my next vertical rectangle, on that particular rectangle, the density is constant. And if the density is constant, where is the center of mass of that rectangle? It would be right in the middle of that rectangle, okay? So if we use our definition of moment about the x-axis, the mass is density times area. For that thin rectangle, it would be density times f of x minus g of x, that would be the length, the height of that rectangle, times dx, times the distance to the x-axis. We said that, so the way the center of mass works is you can pretend all of the area, all of the mass of that rectangle is acting at the center of mass. That's why you can, when you find the center of mass, you can balance an object on its center of mass and it just stays there, right? It's as if all of the mass is acting right at that point, okay? My finger underneath this pen doesn't know how long this pen is. It doesn't know that this pen, how long it goes. It just feels what's directly above it. So you can pretend all of the mass is acting at that point, in which case the distance to the x-axis, it's halfway between f of x and g of x, right? If we're at the middle of that rectangle, how do you find something halfway between two things? You add them together and divide by 2, or times a half. So if I put this all together, I have delta f of x minus g of x dx times 1/2 f of x plus g of x. I can take out the 1/2. Actually, I could have taken out the delta too. Well, no, unless delta is not a constant, right? Delta might not be a constant. But if you FOIL out f of x minus g of x times f of x plus g of x, you get f of x squared minus g of x squared. And this is our alternate formula for moment about the x-axis. And what's good about this is it allows us to keep our rectangles vertical. Allows us to use vertical rectangles. Okay. And that means we can do it for all three, for the mass, for moment about the y-axis, and for moment about the x-axis. We can stick with vertical rectangles. So if I do that, and there's f of x squared minus g of x squared, 1/2, there's my density. Work out the integral, I got 4/7. And then I have all the information to compute x bar and y bar. And after fighting through some fractions, I got 11/18 for x bar and 40/21 for y bar. Okay, we're going to talk about a few more ideas with this on the next video.